We continue our study of volumes of revolution, or volumes generated by spinning an area around an axis. And we continue by looking at a new kind of shape we can get depending on the functions that are provided. Let's look at the region shown here. Y equals root x is one of the boundaries. So let's graph this out. Y equals root x is the square root function. And it's that bent over graph like this. 1, 2, 3, 4, like so. And the other boundaries are y equals 0, so all this, and x equals 4, so right here. So the region we're discussing is the region bounded by those three curves, or enclosed in that zone there. Do be careful how you get the region. It's easy to make a little mistake and have the opposite region or something like that included, but if you're not careful. But with those three boundaries, there's only one region possible. Now, we are going to rotate this around the y-axis. Now, my sketching abilities are maybe a little suspect here, but what we would get is something roughly shaped like this. Sort of a cake pan shape, or a angel food cake pan shape. It's hollow in the middle, comes down and has a meeting point at the center. The y-axis is where we're rotating around, and yeah, it's an interesting looking shape. Our question, of course, here is to use our slicing technology to find the volume of that shape. Where this differs from our earlier example is what kind of shapes we get when we slice. Now, because the rotation is around the y-axis, if we slice horizontally or parallel to the x-axis or perpendicular to the y, we're going to get circular type shapes, but we're not going to get just circles anymore. If we slice like this, little slices delta y thick, each slice is going to look like, well, let's draw it over here, this outer boundary at x equals 4 is going to give us a constant width there, but there's going to be something missing in the center, and so we're going to have a gap. We're still going to have disc type shapes, but they're going to be rings, or some people would call them washers, and it's just a little more involved than what we saw before. The process is the same though. If we can find the volume of one slice, then we're good to go. Definitely one of the ingredients is going to be the thickness, because we have a nice squared off shape in the sense that the third dimension is just an extension of this shape here. Then we're going to get a thickness times the area of the shape. Now, before it was the area of a circle, now it's the area of a shape, but we can work through that. The area of this shape is going to be the outer circle area minus the inner circle area. All of that times the thickness. If I want to know the area of this whole thing, I take the area of the big circle and I subtract away the missing part, the area of the inner circle. Well, that's not too bad, because each of these areas are things we can compute. Pi r outer squared minus pi r inner squared. Those are two separate area calculations. We're going to multiply all of those by the thickness. Okay. If that's the case, now we can go back to our diagram and ask, how can we determine what these two radii are? And this diagram here will tell us exactly. So the inner radius is here. It's the distance from the center of the axis, so the axis of rotation, to the graph. And notice that this boundary here is given by y equals root x. And we also have the outer radius, this one here. And it is a bit easier, actually. If we look at all the slices, each slice, each slice, each slice, this distance from the axis to this point is always what? Well, it's always the same. Every slice always stops at x equals 4. These radii are x distances, and the distance we're going from is from the axis at 0 to the boundary, x equals 4. So the outer radius is straightforward. It is always 4 regardless of the slice. The more interesting radius is this inner radius. The inner radius, which is equal to an x distance, well, it's the x distance defined by y equals root x, or we can replace that as y squared equals x, and that's the x distance we're talking about. X equals y squared. So the radius itself, time goes back to y, but it goes back as y squared. So you have to be careful. There's 2 squareds here. Radius in is an x coordinate. So we take an x squared, but it's that x which is replaced by y squared, and I get a squared there. And our thickness now, we can say explicitly, is our delta y, our little thin slice, delta y thick. Okay, so this gets us almost to the stage of integration, and again, this is the most challenging part for most students. First of all, recognizing which way we should slice this. With this shape, it doesn't make sense to slice vertically. We'd get very, very odd shapes and inconsistent shapes. But if we slice horizontally, we're going to see these rings or washers, circles with a hole, with a circular hole in the middle of them. And finding the area of that to multiply by thickness to get volume is straightforward. We just have to recognize there are 2 different radii to deal with and go back to our diagram and decide how we're going to find those radii. Once we've filled in all those pieces, finding the actual volume is just a matter of integral and dy, as we'll see on the next page. The total volume then is going to be our pi times 4 squared minus pi times y squared squared. All of that times not delta y, but dy now. And our slices start and end where and where. Go back to our diagram. If we're spinning this around the y-axis, so it's like this, and we went up to x equals 4, and if this was y equals root x, then x equals 4 means y equals 2. So our limit of integration, pardon me, would be 2 at the upper limit. And that covers all our slices, and it covers all these pies and squares come from rotating that shape from an area into a volume. And we're ready to go. We can now convert this into an integral problem. Integral from 0 to 2. Pi is everywhere. We'll bring it out front. We have 16 minus y to the 4th dy. And so we have pi 16y minus y to the 5 over 5, evaluated at 2 and 0, and that's going to give us pi 16 times 2 minus 2 to the 5 over 5 minus 0 minus 0. That's nice. And so we get 32, and 2 to the 5 is also 32, so we're going to get 4 pi over 5 times 32. 32 minus a fifth, we'll get 4/5 of 32. And if we want to figure that out exactly, we can grab our calculator. And 80.42 cubic units is a good approximation, numerical approximation, to the volume of the shape we just created by revolving the y equals root x around the y-axis with these other 2 boundaries imposed.